You have learned the key role that activation energy plays in deciding whether a collision will result in a reaction. It would therefore obviously be useful to know then what sort of proportion of particles present have high enough energies to react when they collide. In any system, the particles present will have a very wide range of energies. In the mid to late 1800s, James Clerk Maxwell and Whiteboard figured out how to answer the question, what is the distribution of speeds in a gas at a certain temperature? Their result is referred to as the Maxwell-Boltzmann distribution curve because it shows how the speeds of molecules are distributed for an ideal gas. On this slide, one can see what the Maxwell-Boltzmann distribution curve looks like. One can see that the y-axis shows the number of molecules that have a particular energy, and the x-axis shows the speed at which those molecules are moving that have that particular amount of energy. The y-axis of the curve can be thought as giving the number of molecules per unit speed. There is a long tail to the right end of the graph where we have very few molecules that have a very high energy. In the middle, there's a larger amount of molecules that have moderate amounts of energy. And to the left of the graph, we can see that the graph tends towards zero, as a molecule can't have a speed less than zero, and very few particles have very low energies. The area under the curve is a measure of the total number of particles present. Remember that for a reaction to happen, particles must collide with energies equal to or greater than the activation energy. We can mark the activation energy on the Maxwell-Boltzmann distribution curve. Notice that the large majority of particles do not have enough energy to react. Only these particles that are represented by the shaded green area have energy that is greater than the activation energy and therefore are able to react. In order to get these particles to react, we have to change the shape of the curve or move the activation energy further to the left. One of the ways in which we can do this is to change the temperature at which the reaction occurs. If we heat the gas to a higher temperature, one can see that the peak of the curve shifts further to the right since the average molecular speed increases. As the graph shifts to the right, the height of the curve actually has to decrease in order to maintain the same total area under the graph. As the number of molecules in the container haven't changed, the reaction is just happening at a higher temperature. Similarly, as we cool the gas, you can see that the curve shifts to the left and the peak increases in order to maintain the same area under the curve. One can see that by heating the gas to a higher temperature, we haven't changed the amount of activation energy required in order for the reaction to be effective, for the collisions to be effective, but we've changed the number of particles under the curve that have energy greater than the activation energy, so more particles are able to collide effectively. In this graph, we can see the effect of adding a catalyst to the reaction. Without a catalyst, only these particles under the graph have enough activation energy in order to collide effectively. By adding a catalyst, we lower the activation energy and therefore we increase the area under the graph, and that indicates that there are now more particles that have energy greater than the activation energy, and therefore the number of effective collisions has increased.